student will be able to understand the derivative from a graphical and numerical approach. So in this example, we have a function. I see in this table of values that I'm given multiple x values here on this first column. I am asked to estimate the derivative graphically. Label the point of tangency. Explain the function behavior at x equals a, and give the equation of the tangent line at x equals a. So we're going to go through step by step on how do you exactly do all of this. The first thing is locate the x value. X is my horizontal axis. So in this case, I will be moving 6 units to the left of 0. So this point here that I'm highlighting in red is the point -6, 0. To estimate my derivative, I need to draw a tangent line at this point of -6 equals 0. So remember that a tangent line can only intersect your graph at exactly one point. So here is a rough estimate of what my tangent line looks like. Now I know that the derivative is the slope of the tangent line and I know that slope is the change in y over the change in x. So I'm going to estimate on this line that I've drawn here in red. It's going to estimate another point. It looks like I'm moving 2 up and 1 to the right for every 2 units up and 1 to the right. Again, this is just an estimate, so I'm going to say 2. My point of tangency will be the point that my tangent line is intersecting my graph. So in this case, it is -6, 0. Function behavior at x equals a is related to these vocabulary terms: increasing, decreasing, local maximum, or minimum. Okay. In this case, I see my function is going up from left to right. So my function behavior is that it is increasing at x equals -6. Last of all, I need to find the equation of the line that is tangent to this, the equation of the tangent line at x equals a. So remember, to do this, I am using my point slope formula. So in this case, my y1 is 0, x1 is -6 because I'm using my point of tangency, and my slope is 2. So this looks like y minus 0 is equal to 2 times x minus -6. I do want to clean this up, and I'm left with y equals 2 times x plus 6. All right, let's look at when x is a -4. So here is this point. This point is -4, 2. And my tangent line will actually be horizontal. So I'm no longer, let me go ahead and erase this other line over here. No longer looking at that. My new point of tangency is -4, 2. The slope or the steepness of this horizontal line is 0. Okay? At this point, my function is doing something very special. To the left of this point, it was increasing. And now to the right of this point, it is decreasing. So I'm going to read this special case. If f changes from increasing to decreasing, then f has a local maximum. Now my equation, I'm just going to set this up. I'm going to plug in y1, which is a 2, m, which is a 0. My slope is a 0. And x1 is a -4. So I'm left with y minus 2 equals 0. And if I solve for y, then I'm left with y equals 2. So what this is saying is the equation to this red line here is y equals 2. I'll do one more example and then have you all do a few where I can check for understanding. My next x value is -2. So I should be looking at -2, 1. This is my new point of tangency. I'm going to draw a rough estimate of my tangent line, which means I can only intersect the graph at one point. So I'm going to try to draw this out. This is kind of challenging. Okay, so there's a rough estimate, right? All right, so I'm really trying to get the exact direction. What is the exact direction of this point of this point of tangency here, or at this exact instant, what is the direction? I'm trying to capture that. So now, using this rough sketch, I will choose a couple points here and here. And I will estimate the slope, which is about 2 down to the right, maybe about a -1. I see that my function from left to right at this point is going down, so it is decreasing. And now I'm ready to plug in y minus 1 is equal to -1 times x minus -2. So my equation I'll write out here is going to be y equals -1 times x plus 2 plus 1. So now I'm going to have you all do a few of these examples. Actually, 4. So the one problem that I would like to go over is when x is equal to 1. In this case, this is a special point because my function is switching from increasing to decreasing at this point. So my derivative estimate here, my slope should be 0. My point of tangency is 1, -4. Function behavior is a local minimum. And my equation, once I plug in this point and my slope, will end up being y equals -4. Next, we're asked to draw the tangent line on the graph at each point to estimate the derivative. Then we are going to do something new. Determine if the derivative is less than 0, equal to 0, or greater than 0. In other words, is my derivative negative or is my derivative positive? So f prime of -8. I should be looking at this point here. And if I were to draw my derivative, which is the slope of the tangent line at that point, I can see it's clearly going down. It is a negative slope. So my answer to this first question is f prime of -8, is less than 0. Go ahead and try f prime of -6. So we see we should be looking at this point here, which is clearly a local minimum, which means our tangent line is horizontal and has a slope of 0. Let's next look at f prime of -4. Go ahead and answer that question. So if I were to draw a tangent line here along this function, I can see my function is increasing here, which means I have a positive slope. In other words, f prime of -4 is greater than 0. Here is f prime of 7. Should be looking around here. So for f prime of 7, this shape looks a little bit interesting here. Okay. I want to very quickly review what a cusp is.